Okay, so let's do the second problem this time. So we have a long shunt compound generator has the following parameters. So armature resistance is given, RSE, RSH. The machine supplies a DC load of 10 kilowatts. At this load, the armature generates 246 volts. Determine the terminal voltage. So first things first, so we have to draw the circuit. It's a long shunt compound generator. So for a long shunt compound generator, so if this is your armature, then we will now have the series field resistance there because it's long shunt, and this one is your shunt field. There. Let's write the values. So our RA is 0.1, 0.1. Our RSE is 0.05, and our RSH is 120 ohms. There. We are supplying a load of 10 kilowatts, so of course the load is tapped across the terminals at the output. So this is your load. There. It's rated 10 kilowatts, so 10,000 watts. And what else do we know? At this load, the armature is generating 246 volts. So you have a generated EMF. When it's applying that load, it's generating 246 volts. There. So the question is, what is the terminal voltage? So we are being asked to solve for the terminal voltage, which is basically this. This one is our terminal voltage. There. So how are we going to solve for the terminal voltage? So remember that this terminal voltage right here multiplied to your line current, which is here, should give you your output power, which is 10,000 watts. So which means to say we can have an equation for IL being IL is the quotient of 10,000 watts divided by the terminal voltage VT. There. And what comes after that? We know that that terminal voltage is also, if we're going to there, I'm just drawing the polarity of that voltage. Similarly, since there is no component in between these terminals and this field, that only means that this voltage is of the same potential difference as that across these 2 points. So this point is the same as this one. This point is also the same as that one. So The voltage here is also the terminal voltage. That should imply that the current passing through this, which is going to be downwards, and which is now called your ISH, can be written again in terms of VT. So ISH, this is simple Ohm's law, is voltage VT divided by your resistance, which is 120 ohms. There. And lastly, we also have what we call here your armature current. Your armature current is the current passing through your armature. So if I call that IA, note from your previous basic electrical engineering course, this is a series circuit right here from one node to another, which means to say there is only one value of current passing through it. So if this is IA, then this is also IA. There. Now, if we're going to write the polarity again of the drops, then this must be plus, minus. This is plus, minus. There. So I'm actually preparing myself to write a KVL equation across this loop. So this is the loop that I want to consider. I'm going to call that loop A. And we can now write our KVL equation there. Again, making use of the exit polarity rule. Let me just label this equation to be equation 1, this equation to be equation 2 before we proceed. There. So, writing now our KVL equation at loop A, exit polarity, exit here is going clockwise. We're going clockwise, okay? Going clockwise. Exit there is positive, so positive. The voltage is 246, so no problem with that. Next, exit here is negative, so this must be minus. The voltage here is 0.1 times IA, resistance times current. So 0.1 IA. And then next, through this component, exit polarity is minus again. Voltage is resistance times current. So that's 0.05 IA. Next is the voltage across this component. So this is minus. Voltage here is VT, as we've talked about already earlier. It's VT. Sum of voltages must be 0. There. So what do I have here? I have a value of IA in terms of VT. And what will that be? Your IA. So if I transpose everything, that includes IA at the right side. So you have 0.1, positive 0.1, positive 0.05. That should give us 0.15 IA, right? So at the left side, we have 246 minus VT. And at the right side, we have 0.15 IA. I'm going to get rid of that 0.15 coefficient by dividing it, cross-multiplying it from the 246 minus VT side. So IA is 246 minus VT over 0.15. And I will call this equation 3. So now we have 3 equations. Before I continue, I will change the color of my pen because I want to change the color of my pen. Okay. So looking at this node, again, I will name this node just for the discussion purpose. Just for the purpose of having a clear discussion. So I will label this node as X because I will do a KVL equation there. And as if you are following with how I'm trying to solve this problem already, the currents involved entering and leaving this node are IL, ISH, and IA, which were all written in terms of VT. So I can now construct an equation which purely involves VT. And from there, we can easily solve for VT already. So let's do KCL at node X. Okay. What are the currents entering node X? So we have here IA. How about currents leaving node X? We have IL and ISH. Now, instead of writing IA, I will make use of equation number 3. I will write 246 minus VT divided by 0.15. Next, instead of writing IL, I will make use of equation 1. So IL will now be replaced by 10,000 over VT. And lastly, instead of writing ISH, I will write from equation 2 VT over 120. And I now have established an equation which purely involves VTs. And I will be able to use this equation, of course, to solve now for VT. If we're going to do this manually, this will become 246 minus VT divided by 0.15 is equal to, we will have a common denominator here equal to 120 VT. 120 VT divided by VT is 120 times 10,000, which is equal to, I don't know, 1, 2, 0, then 4 zeros, 1, 2, 3, 4, there, which is equal to 1.2 million. And this one becomes 120 divided by this times VT squared. There. And next we can cross multiply the denominators to the left and the right side of the equation respectively. So I need my calculator right now. 120 times 246 should be 29,520. this times this obviously is minus 120 VT squared. This times that 1,200,000 times 0.15 is 180,000. My dogs are hungry. I just fed them. Plus 0.15 plus VT squared is 0.15 VT squared. So it looks like a quadratic equation that we're going to have to solve for VT. If we continue this, we transfer everything to the right side of the equation. So 120 plus 0.15, we have 120.15 VT squared. And then minus 29,520 VT plus 180K. This should be equal to 0. So we have a quadratic equation. Your calculator can easily solve that. So put your calculator in equation mode. For mine, it's an equation mode. Polynomial. Degree must be 2. Then we have to input now your coefficients. 120.15 negative 29,520 and 180. Okay, we're going to have two answers here. One is 239 and the other one is 6. Of course, we will be choosing the more sensible answer. So looking at the generated EMF, which is 246, it's impossible for us to have an output voltage. Remember, the terminal voltage is here. So it's very impossible for us to have a voltage which has a value of 6. That's a very low voltage compared to the generated EMF. That would only mean the voltage drops here must be very high, which doesn't make any sense because the voltages here are just 0.1 and 0.05. I mean, the resistances here are just 0.1 and 0.05. So that's a very low value of resistance to cause such huge amount of voltage drop. So the more sensible answer must be the first one, being 239,000.436. There. So that must be the terminal voltage of the long shunt generator. Thanks for listening.